And now what you may wonder is, are there any restrictions on what the complex numbers A0, A1, B0, and B1 can be? So I suggest that you pause the video for a moment and think about what restrictions we might need to enforce on these 4 complex numbers in order for U to be a valid single qubit quantum gate. So here is the answer. First of all, the 4 complex numbers should be such that the resulting transformation U maps ket0 to some other valid qubit state, and similarly for ket1, this is mapped to a valid qubit state. Now recall that qubit states are valid as long as they correspond to vectors which have magnitude or norm equal to 1. And now in particular for the first output qubit state, this is the case if the magnitude of A0 squared plus the magnitude of B0 squared is equal to 1. And for the second qubit state, it is the case if the magnitude of A1 squared plus the magnitude of B1 squared is equal to 1. Now the other condition that we want, which you might not have anticipated, is that the transformation U should preserve orthogonality. What this means is that if 2 vectors are initially orthogonal, then their images under the quantum gate U should also be orthogonal. And now since ket0 and ket1 are orthogonal when interpreted as vectors, so they're 1, 0 and 0, 1 respectively, then we want their images, so respectively A0, B0 and A1, B1, to also be orthogonal. And now I want to emphasize that this second condition is not something that we have deduced from anywhere, but rather it is just a rule of quantum mechanics. So quantum gates have to be such that they preserve orthogonality. So in summary, a single qubit quantum gate is a linear transformation from states of a single qubit to states of a single qubit. And additionally, it must satisfy the 2 conditions. One is that, of course, it must map valid qubit states to valid qubit states. And secondly, it must preserve orthogonality. So if 2 vectors are orthogonal, then their images under the quantum gate must also be orthogonal. And conditions 1 and 2 define what is known as a unitary linear transformation. Now, of course, the name is not important to remember. What is important to remember is that all quantum gates are linear transformations that satisfy these 2 properties. So these transformations are called unitary transformations. And I just want to remark that even with these constraints, there are actually an infinite number of possible single qubit quantum gates. So here is another example of a single qubit quantum gate. It's called the Pauli Z gate, whereas the quantum NOT gate was the Pauli X gate. Now the Pauli Z gate acts as follows. It maps ket0 to ket0 and maps ket1 to minus ket1. So in other words, it does nothing to ket0 and it applies a phase or a factor of -1 to ket1. Now, first of all, let's do a sanity check to verify that the Pauli Z gate is indeed a valid single qubit quantum gate. So we need to check that the 2 outputs ket0 and minus ket1 are indeed valid single qubit states. So ket0 certainly is a valid qubit state, minus ket1 is also a valid qubit state. And now the second condition that we have to check is that ket0 and minus ket1 are orthogonal, or rather the vectors that these 2 states correspond to are orthogonal. And this is indeed the case, and if this is not immediately clear to you, think about the fact that the 2 standard basis vectors are of course orthogonal, and moreover notice that any multiple of the 2 standard basis vectors are still orthogonal. So if you multiply the first standard basis vector by any scalar, you multiply the second standard basis vector by any scalar, then the 2 resulting vectors are still orthogonal. In particular, minus ket1 is just the second standard basis vector multiplied by the scalar -1. And if all that I've just said is not immediately clear to you, I suggest that you pause the video and work this out on your own as an exercise before you proceed, because this is very important. So here's a simple exercise for you. So consider a state psi, which is alpha ket 0 plus beta ket 1. You're asked to compute z applied to psi.